Okay, so we have seen we can do hidden addition, hidden multiplication, and hidden constant, and we can prove it. We can prove it without knowing. So we have constant variable, constant addition, and that's where we stopped last time. What kind of things that we can do with that? How about permutation? So now this slide is now very clean because all the dirty things are now hidden in the slides before. So we just have to argue about addition and multiplication. So I can prove to you that two numbers are permutation of two other numbers. So what I do is I write down these. I prove to you that S is A plus B, that S is C plus D, that P is A times B, and P is C times D. Yeah. And okay, S is short for sum and P is short for product. So I prove this property. And this way, this has only two solutions, that AB is equal to CD because it has the same product and the same sum. Yeah. Or I have permutated them, that AB is DC because product and sum don't care about the order. But this is the only solution for that. So there is no other solution for this equation system if you solve it for AB, when AB is either CD or D times C or DC. So what we have proved is that we have permutation of two numbers. But I have here in my number, I have two numbers, and here's another commitment that also has two numbers, and they could have changed the order, but it's still the same two numbers. So it's a proof of permutation of two numbers. Yeah? Zero knowledge proof. I don't.
But no number can be zero for this one.
If I multiply, the sum is, so A is 0 and B is 1. So this is 1 and this is 1 and this is 0 and this is 0. So either A or B is 0 and the other one is 1. Yeah. So it works also for 0. And for 0, 0 it also works. So, okay. So, that's an exercise you can do, but you can see that this is the case because it's the equation. If you write down the equation, when there's only one way to solve it, two ways to solve it. Now let's do Boolean circuits. Okay, so we can prove that it's a permutation. How can I prove that A is 1 or 0? Yeah. This is permutation. Yeah. So they switch the position. Okay. We had this in advanced encryption standard and nobody complained. But good that we sorted this out. And sorting is also one kind of permutation. Yeah, so that's okay. I want to prove that A is either 0 or 1, but I don't want to reveal A. So what I do, I can do the following. I can prove that A and not A is a permutation of 0, 1. So here I store two numbers in my hidden statement, and here I publish 0 and 1. I can publish 0 and 1 and prove that this is a permutation. Yeah. So now that means this is the case. So I can also write it this way. I just write this one. That A plus not A is equal to 1, and A times A is 0. Okay, that's wrong here. 0. Okay. Which also proves that this is now either 0 or 1. And 1 is 0, the other is 1. You can do the negation. Negation is easy. So first you say these are two Boolean numbers, and when you say the sum is equal to 1. So when this 1 is 0, and the other must be 1, because we already fixed that this is the case. You can do and is A times B is equal to this one. So that's multiplication. You know, if you have 1 and you have the same thing, and you could also do the inverse, but no, you can also do OR and use De Morgan. So you can use the knot of the end of the knots, which is you prove this here. And which is just an arithmetic formula which proves that if A and B are Boolean numbers, you do the negation, you do the AND, and then we do the negation. And this is only true if A or B holds. Okay, so this is also quite obvious. So now we have zero knowledge proofs for doing Boolean operations. And what can we do with Boolean operations? The computer scientists would say everything, because computers are built out of this. So we have zero knowledge proofs for every polynomial time computable function. We can prove that a certain property holds as long as we can build a circuit for it, which is nice. So because we don't have to think about addition and multiplication anymore, because we know we can emulate Boolean functions and we can prove Boolean functions. And yeah, that's the idea, is we transform it in Boolean circuit, and then you have a zero knowledge proofs for all these operations using this hidden multiplication, hidden addition, and so on and so forth. This was the state of research until 6 years ago, that you basically can make a zero knowledge proof about everything that you want to do. The only thing is that you have to build a Boolean circuit. And I remember that somebody applied for the open position for security and privacy here at this university, and he was actually finding out smaller circuits to get better zero knowledge proofs. To reduce the circuit smaller and smaller and smaller, so that we can have zero knowledge proofs we don't take too much time. Yeah, so that was one line of research. Yeah, yes. That C is what? Yeah. So that's. Yeah, you can maybe do some simplification here as well, but just this is about what we can do. Okay. So, and now we talk about time. So we have complexity measures, and we are leaving the book of Delfs and Knebel by now, or maybe even some slides ago. So if you want to have more knowledge about the things that we do for the next 15 minutes, you can see the lecture notes of Justin Taylor, I don't know if it's German or not, proofs, arguments, and zero knowledge, where I took the next contents out, and it's on Elias. You can download if you can look it after. But I think the slides should suffice. Now we talk about communication complexity, the number of size of messages which we have to send forth and back, which is, if you do a Fiat-Charmé heuristic, is also the size of the things you have to publish in order to do that. Round complexity could be a thing. How many rounds do you need to do it? We have reduced the round complexity drastically by using the Schnorr proof instead of having all these kind of loops around 50% decisions. And we can even go from interactive zero knowledge proofs to non-interactive zero knowledge proofs using Fiat-Charmé heuristic. That's also something we did. And then another point is computation complexity. We want to have, well, doesn't need forever in order to do the evaluation. Just imagine you want to make a zero knowledge proof for the election in Germany. Yeah, you have some 30 or 40 million voters, and you want every voter participates in a zero knowledge proof, and you want to make sure that your vote is counted, that they count your vote, but it's not published. Yeah, so you basically, the government has a zero knowledge proof that it counted your vote in the correct way, and you have to prove that you casted your vote in the correct way. This is possible. We can do a zero knowledge proof for elections. Now, it's a nice application, because you want to have your election secret, and the government, and you want to be sure that the government doesn't know who you are, what you voted for, which is not, at this moment, we need trusted 1,000 parties which are sitting in the ballots and counting. Yeah, that's a nice application. And there's a lot of research doing this since there was this election of Bush versus Gore, where they had some problems with counting votes. And we could do this electronically. Okay, so first step to do this is the same slide, so nothing new. First step is it's also the same typo here. Let's just prove it's the same slide, so without knowing. So the first step is hiding commitments, of course. And yeah, so let's work with, so first thing, good thing is about hiding commitments, it's one number, it makes it very efficient. But can we work with that in an efficient way? So one way to do this is, yeah, we want to prove that we know everything in the hiding commitment. So we want to prove that the hidden commitment contains this other hidden commitment. So like getting everything out of this hidden commitment, and we still have the same thing. So what we can do is we make a Zillow proof that the new commitment has the right form of powers of h and powers of g. Then we make a random, and this is done in the first round here. Then we choose a random Rn and send here somehow in h to the Rn plus 1. And when we get the challenge, the sigma proof again, and then we can send this information. And what the other party does is it takes the big assignment, divides it by the product of the other hidden assignments, and should get some kind of power of h only. And this is how you could sort this out. Yeah, so you sort, you want to prove that this has this kind of form and that you know all the powers, and there are so many in this inside, and this is how you can do it in linear time. Which arises the question is, can we do this better? Can we do this better? Yeah, so here we prove that this is a power of h of b, so that this has this property, and so that works. So it's just the power of h to the b. Yeah, because this is committed, and we give an exponent which says which power of h to the b it is, and here y to the c is now only a power of h, and this is Schnorr proof to do that. Now, in order to do this more efficient, we need some technical lemma, which is so-called Schwarz-Zippel lemma, which we don't use this explicitly later on, but it's a very useful tool which helps you to prove that something happens with very small probability. Okay, so we have any field, and we have a non-zero m-variate polynomial. So we have m variables, and the total degree is at most d. So basically, you could have something like xy times y plus z is equal to 0, something like that. That's a 2-degree free variable polynomial. Now, Schwarz-Zippel lemma says the following. So if you take any set out of this field and you choose this randomly out of a set, the probability that this polynomial is 0 is the degree of a polynomial divided by the size of a set. It's not s to the m, it's just s to the s. So, and if x is uniformly drawn from s to the n. So I give you one example, which may be easiest one example. X is equal to 0. Yeah, there's only one way to do that. X is equal to 0. So probability of x is equal to 0 is 1 divided by whatever you have. And it could be even 0 if it's not the case. Yeah. So now you could think of 3 times x plus 1 is equal to 0. There's one solution for that. Now, if you think of higher polynomials like x squared plus 3x plus 5 is equal to 0, then you have a parabola, and the parabola has 2 solutions. And if you take to the power to the third, you have a cubic function, and a cubic function has 3 solutions. And this is also the case in a field. So this is somehow related to the fundamental theorem of algebra, but a polynomial of degree d has exactly d solutions, even counting double solutions. And when we have a set which is making it smaller, so we have a degree of a polynomial divided by the set you are drawing from. And it could be less because maybe your roots are not in the set or you have double roots. So we don't prove that. The proof is actually not too hard to do it, but there's some examples. So for example, here, the probability that for some reason you get, you draw a random a root of something. So the question, do we get a root of y? We have two roots, and we probably are 2 divided by p if you take from false space. That's one application. This gives you also some other kind of information. For example, if you're looking for the third root, then this gives you information where only 3 roots in order 3, even if you do this modulo p, which is a nice application. And one application is you want to check 2 polynomials that they're identical or not. You have a complicated polynomial on the left side, a complicated polynomial on the right side. Best thing is to just put some random numbers into it. And if they're equal, then you are really lucky if they're not equal. It even holds for real numbers. So assume that you have 2 polynomials, left and right, and you want to check whether they're the same. Then the probability that they accidentally are the same is the degree divided by the size of the real numbers. How many real numbers do we have? Infinitely. So it's, if they're the same, then you have it with probability 1. And they're accidentally wrong even if they're not the case. So either they're the same or not. Because if they're the same, then this p minus q is a polynomial of degree 0, and then this doesn't hold. Okay, so that's a Schwarz-Zippel theorem. It's really nice. And we use that in order to prove now the generalized Petersen commitment. And we start with the non-hidden version. Okay, the non-hidden version. So, and this is the first bulletproof that we do. We do 2 bulletproofs. That's the first one. It uses a very nice trick. So what we want to prove is that we know the exponents of all these things. We want to prove that, but with log n rounds. Yeah. Not with linear number of rounds, with log n number of rounds. So what we do is we do a commitment, which is just the thing that we know before. And we have these generators where in a relationship. And this is the algorithm. So prover does the following. If n is equal to 1, then just do the Schnorr proof, because we just have one exponent, and we can send a random number, g to the random number, we get some challenge, c, and then we compute b times, what was it, u1 times the challenge plus this random number. Okay, so that's done. Okay. If u is not 1, and we assume that n is the power of 2, so you have 2, 4, 8, 16, and so on, we do the following. So we split the vectors in 2 parts. So the exponents are split into ul and ur, and the generators are also split in 2 parts. So basically, you take half of them. Now what you do is you send VL, which is, now this notation needs some explanation, is that you have, where is it on the next slide? Here. So GL is this. So you take from the right side of the generators, you take u to the power of I. So that's the notation that we're using here. So this is a vector now. UL is still a vector. And you take the right generators and take it to the power of UL. And here you take the left generators and take to the power of UR. Why we do it, we will see in a second. Okay. So this is a commitment that we do. So we receive, this is one number because it is the right side, the generates from right side multiplied with the exponentiation of the left side. So it's that flipped positions somehow. And vice versa. We send those, so we have two numbers. We send two numbers, VL and VR, which are from GK. So that's just two numbers, GQ. Okay, now we get a challenge versus alpha, a single challenge alpha. And now we do something crazy. We take the first commitment, multiply the left commitment, with garbled commitment, and take it to the power of alpha squared. And we take the right side and take it to the power of 1 over alpha squared. Modulo Q minus 1, modulo Q, of course, in the exponent. Okay. Then we compute two new vectors. So this is a vector again. This is a vector of size n². We take the first part, multiply with alpha, and the second part divided by alpha. And this is the craziest thing. We compute new generators. So, and then we do this recursively. So what we're doing is basically, so this is still okay that you take some vectors and somehow fold it and you have some random challenge. This is something that we used from Schnorr proof. But this is really changed is that from one recursion to the next one, we changed generators. So what do we know about generators? We can multiply two generators and get a new one. Now, this is fine. It's something we can do. However, we are losing the nothing up my sleeve property. That's the thing that we lose, because now we know the relationship between the new generators and the old ones. Okay, so here on the other side, we can send this information and optionally check it. I say optionally because the Rayfair has already the information to do it on his own, so it doesn't even need that. So we don't need this communication at all at this point. And then we do this recursively. So what happened is we started with an array of length n, and what we did is we folded this array, we split it in two halves, somehow combined it, and then we have a new array of length n². So here this is G is somehow, G and U are vectors of length n, and here it's only n². So we're halving it. And that's why we choose n to be a power of 2. And then do it again and again and again until it's a single number, and then we check it's the same. And that's the idea of a bulletproof. So bulletproof takes some task which is linear and reduces to half of the size to different tasks with different generators and should be still the same, which is something they came up in 2018. So it was not so long ago. Probably we were already alive in 2018. Probably you weren't alive when zero knowledge proofs were invented, but this was a breakthrough. Okay, so first thing we want to check is, does it make sense somehow? Does it work? And for this, we do the following. So this is the notation for witness. So this is the exponent, and these are all of them, and this is the left half, and this is the right half. Okay, so far so easy. These are vectors. And with generators, we do the same notation here. We have all of them, we have the left side, and we have the right side. So far so easy. Now, in each recursion, we get the challenge alpha, and we compute new generators, which is those from the left side. So you take here G1 to the power of alpha minus 1. It's here. It's G1 to the power of alpha minus 1 and Gn plus half plus I to the power of alpha. So that's how each of these generators is generated. They are constructed from a vector G, of course. Yeah. So do not use G and G prime ever together. Yeah. Don't do that. But there's one trick. Now these are somehow related, and the verifier and I know that they are related somehow, but if I take two of the new ones, and compare them to each other, I still don't know how they're related, because we're using both the unrelated ones. So it just gives us some connection with the past, but not to each other. Because you start with all of them, and then you combine these, something like that, and then you combine them again, you combine these, and then you combine that. So and then you have the generator of the last round, and if they are not connected in the first round, you just have more connected ones combined into new ones. So in each round, they are not connected to each other on the same level, but they're connected to the higher level. So never use them together with a higher or lower level. But we just use it here for this proof and never more. So that's the first thing we have to make sure. Okay, now for the intermediate commitments that we produce is that we take, here this is the formula, you take the product of I to n½ and you take the right side from the index to the power of the left side. And that's the same thing you do here on the other side. So this is the thing that you do. And the question is, first question is, does it make sense? Yeah. We can do lots of calculations, but at least if the statement is true, then the verifier would say, okay, it's true. But it shouldn't be that the statement is true and the verifier says, no, I don't believe you. So that's called completeness. So we have to check for completeness that if we follow the protocol, that the verifier comes to the same conclusion. Which boils down to the question is the new commitment G prime to the power of U prime, is this true? Is the new commitment true? Or is it something else? And this also gives some insight why we do these strange things. Okay, so G to the U prime is defined as, so G prime, so this is the definition of a new thing. So I plug in this value and take it to the power of U prime. So I have this is this definition to the power of, and U prime was defined as, it's here. U prime is alpha times UL plus alpha to the -1 times UR. So which is we plug in here on this side. Somehow missing on that slide. Okay, and now I can do multiplication. Okay, this multiplication I can put outside, which is I've done here. And then I have alpha to -1 times alpha times UL, so I get this term. I have alpha to -1 to alpha to -1 UR, I get this term. And I get this term, like here, because alpha and alpha to the -1 are vanishing now. So what we get is we get GL to the UL, the left side to the left side, times the right side to the right side, which is this commitment here. Here. Because that's CU. CU is the left side to the left side, the right side to the right side. And here, these are now and these are exactly the things which are coded in here, which is GL to the power of UR. I just switch positions here, and this is, which is VL, and this is GR to the power of UL, and I switch the position of alpha squared. So that's left side and the right side. It was defined the same way. So that means from one recursion to the next recursion, I start with a true commitment, and the next recursion, I still have a true commitment. So I start somehow meddling with the equation, combining them, and get a new equation. By the way, the new commitment is still one number. So we haven't changed the number of numbers. We just changed the number of elements which are in a representation of this new number and combine it somehow. So how do we convince the other person that this is the case? Okay, So this is all. So let's call it the soundness proof idea. This is just what we can refer to it. So if you look at this exponent here, okay, should have asked him to fix that too. So if you look at this exponent here, so what we have is that if you multiply this to the power of alpha squared, okay, we multiply with alpha squared. Need larger gloves. Alpha squared. So this is basically a polynomial of degree 4. If I take this to the power of alpha squared. Alpha is given by the verifier, or later on we have a hash function doing this for us. So we have a polynomial of degree 4. So this has 4 solutions. There are 4 numbers which fit this description, depending on alpha. Now, we have 4 numbers, so you have 4 chances to guess it correctly. However, we have to guess it correctly with respect to the whole space of GQ. And Q is a large prime number. So the probability that we guess this correctly at the beginning is very small, and VL and VR are random numbers. So that means that this is the chance that by chance you have a correct value. And this is just this intuition. So the prover gives you the exponent, and now we change the exponent and combine it. And this is something I basically announced, that we do exponentiation in the exponent at some point. And this is only to the power of 2. Because later on, we do it to the power of n, of course. And then we have a to the b to the c in order to do zero knowledge proofs. Okay, that's just the soundness proof idea, why we need Schwarz-Zippel in order to this. Now, there are some observations. So if you look at this protocol here, you don't have to send this, because you don't have to send CU, because he can compute that. He knows alpha, he knows VL, he knows VR. So why should I send him something that the verifier send something that he knows? But you have to send VL and VR, which is essential in order to make sure later on that everything has transformed the correct way. If you don't send this, then the proofer can cheat. Okay, so that's first observation. But the question is, if you don't send this, then in this round there's no test. Here we don't check it anymore. We don't need checkings anymore, and there's only one check, which is in the last round of Schnorr's proof. So in the last round, we prove that's correct, and this proves everything up to this recursion. So boils down to one question, one test. Okay, which is also nice, so we don't have to do a lot on the verifier side. Now, if n is not the power of 2, just add zeros. Okay, that's also easy. And we can easily modify this to a hidden Petersen commitment. Very easy, because what you do is that the odd ones are random numbers and the even ones have information. And every time you fold it, you have one of them left until the last step, and then you do the hidden proof at n equals 2. Because that's already, if you look at this problem here, you could say, you know what, every second one is hiding something. And by folding it together, you still have every second one is hiding something, and then you have already the hidden commitment, and you don't have to do this strange operations that you had before, which is nice. Okay. So that's one property. We can use Fiat-Shamir heuristic in order to do that, just by putting alpha into a hash function and do that. So you have a non-inductive variant, and the best thing is the complexity. The number of messages is logarithmic, and also the number of messages for non-inductive variant is logarithmic. Like Schnorr's zero knowledge proof, is only computational zero knowledge, and so you can prove that it's computational zero knowledge, and you can just refer to this lecture notes, because we're running out of this time of this lecture at some point, and this is only an introduction to cryptography. If I remember correctly, it's not an advanced course in cryptography, but maybe I'm too far anyway. Now, That's just the start. That's the easiest bulletproof that we do. So we have 2 more to go. Because the next thing we do is product. And in order to do the product, we have to know what kind of product we are talking about. And we're talking about something which is commonly known as convolution or folding product, scalar product. So you have 2 vectors. And what you do is you multiply the first one with the first one plus the second one times the second one, and so on. Yeah, so that's what you do. And so you get one number at the end. And we use this notation in order to denote that. And what we want to do is we want to have an efficient proof for this. Yeah. Now, of course, we can do it already. Now, what you do is, we copy all the statements down and say, okay, I have a hidden commitment for A1, AB, and so on. And then I prove the product, and then I prove the sum, and then I have a linear zero knowledge proof that proves this property. So doing this is something we can do right now using Schnorr's proof and with hidden commitments. If we are giving this number and G, H, and U are this nothing up my sleeve generators again. So and U is just one of them. Oh, this is wrong. This is just U to the C. I don't know why I put it there. Probably last. Don't do any. So U is just a number. This is just one number. Okay. So there's a linear size proven. But now the punchline is we can do this in log and rounds as well. Yeah. So with this technique. So this is by Vincent and others. So this was published in 2018 in this article, Bulletproofs, Short Proofs for Confidential Action and More. And in order to make these slides, I had to go to this paper and put it on the slides. So, but usually students complain that they want to see the new stuff, and the exciting new stuff. Okay, I just want to. We don't have a lot of time left, so we probably have to talk about this next time. I want to show you similarities to the things that we have seen before, and what is a statement. So we have a commitment here of A, B, and C, and we want to prove that C is A times B, but in this strange way. Now the similarity is that if n is equal to 1, we can solve that in a constant number of steps. So that's the same structure as we have seen before. And if you look here at this point, we have also the idea that we do a recursive run. And we have decreased the length of vector A and the vector B and the generators G and H to half of them. It's also the same that we've seen before. So what we do is we split these vectors, we split these generators. This is also something we've seen before. We have a challenge. So we have some commitments that we have to do before. Again, we have strangely combined left and right somehow with these 2 statements here. So this is somehow magic coming that we have some parts from the left side combined with some parts of the right side, and we send this to a verifier. Then we have a challenge X. X plays exactly the same form of alpha in the alpha proof. And then we compute G prime and H prime. And this is again, as in the last proof, is something that we can do together. And then we take the last commitment and change it to a new commitment. And we have new generators again. So also we take new generators, generators to the power of x here and to the x minus 1. And this should be a multiplication. So that's a mistake here. Plus doesn't make sense. This must be a multiplication. Okay, so that's the generators. And then we do some magic with the new coefficients where we have the left side combined with the right side. And so we go from an n vector to an half vector here at this point. And we do the same thing for A, B, and C is just a number. So this is just one number to one number. So this is 1 to 1. So that is what happens in this folding product. And so the idea is you take the folding product and somehow, like in the vector proof, you make this happen, but this goes smaller and smaller and smaller. And yeah, so that's something we will look into next time. And then we make the next step, because it's just a folding product. The next step will be that we take a lot of folding products. We write folding products under each other. And then we fold the folding products again together. Yeah, so we have a folding of the folding products, which on the bottom line means that we can do everything in logarithmic number of rounds. And that will be the conclusion of the lecture, because we don't get any farther. But basically, with this coming of this bulletproof argument that we fold the vectors together, we will get zero knowledge proofs for every statement that we can do with logarithmic number of messages, which will be something that we do next time in order to motivate why we want to do this in the first place. And that concludes for today. I thank you for attention and see you. First day exercise.